Imagine a structure so daring it looks like a glitch in the Singaporean skyline. Marina Bay Sands isn't just a hotel, it is an $8 billion gamble against the laws of physics. Towering over the reclaimed marshes, three 55-story towers support a massive 340-meter-long sky park, a cantilevered marvel that shouldn't logically stand. How did engineers prevent these leaning towers from simply collapsing inward under their own immense weight? This is not just a construction story, it is a masterclass in structural innovation, where every single millimeter was fought for against the relentless pull of gravity. Today, we peel back the glass and steel to reveal the hidden. The story began with a visionary challenge: create an icon that redefined the concept of a city skyline. Architect Moshe Safdie drew inspiration from a deck of playing cards, envisioning three separate towers that curve and lean until they meet. The Singapore government demanded something spectacular for their new integrated resort. But turning a deck of cards into a 300-meter-tall skyscraper presented immediate geometric nightmares. The towers had to lean at an extreme 26-degree angle, making them some of the most complex vertical structures ever attempted. Critics called it an engineering impossibility, yet the design was approved, setting the stage for a race against time and nature. How do you build a curve that starts? Before the towers could rise, engineers had to conquer the ground beneath them. Marina Bay is built on reclaimed land, essentially a mixture of marine clay and soft soil that behaves like liquid under pressure. To stabilize this, crews dug massive diaphragm walls, descending 60 meters deep into the earth to create a giant underground bathtub. Over 20,000 tons of steel reinforcement were lowered into these trenches before pouring concrete. This created a solid foundation capable of supporting the 500,000-ton load of the towers above. Without this subterranean fortress, the towers would have sunk or tilted unevenly, turning the dream into a catastrophic disaster. As the towers climbed, the real challenge emerged: the lean. Each tower is split into two halves that curve toward each other. The western legs lean at a staggering 26 degrees, an angle so steep that they would have toppled during construction without external help. Engineers used temporary steel struts and massive tension cables to anchor the leaning legs as they grew. These cables were constantly adjusted to counteract the increasing gravitational pull as more concrete was poured. This was a high-stakes balancing act, where even a tiny miscalculation in tension could lead to structural failure. The workers were essentially building two separate leaning skyscrapers that had to meet perfectly at the 23rd floor. Achieving the connection between the two leaning halves was the project's first major climax. To lock the structures together, engineers used heavy-duty steel trusses and post-tensioning techniques. Once the two halves met, they shared the load, creating a stable, arched A-frame. However, this introduced new stresses. The internal concrete cores had to be thickened significantly to withstand the lateral forces trying to pull the towers apart. Specialized monitoring sensors were embedded throughout the concrete to track movements in real time, allowing the team to adjust the building's geometry as it settled. This iterative process ensured that by the time they reached the top, the three towers stood perfectly aligned. Floating 200 meters above the ground, the Sky Park is the crown jewel of Marina Bay Sands. It is longer than the Eiffel Tower is tall and stretches across all three towers. But you cannot simply place a 340-meter-long steel platform on top of three independent skyscrapers. Why? Because buildings move. Wind, heat, and seismic activity cause the towers to sway independently. If the Sky Park were rigidly attached, the stress would rip the structure apart. To solve this, engineers designed the park as a series of separate segments connected by massive expansion joints. These joints allow the towers to dance in the wind, while the park remains a seamless, unified pair. Lifting the Sky Park into place was a logistical feat of epic proportions. The structure consists of 14 main steel bridges, with the largest segments weighing over 700 tons each. Standard cranes were useless at this height and weight. Instead, engineers employed heavy-lift strand jacks, the same technology used to raise sunken ships. Over several weeks, these massive hydraulic systems slowly winched the steel sections up the sides of the towers at a rate of just a few meters per hour. It was a painstaking process, where even a slight gust of wind could cause the massive steel plates to collide with the glass facade. Precision was paramount, as each piece was... The infinity pool is the park's most famous feature, but it is also an engineering miracle. Holding nearly 1.5 million liters of water, the pool spans three separate building segments. To keep the water from spilling out or the pool from crocking as the towers sway, engineers used a specialized stainless steel shell. This shell is supported by 4 unique movement joints hidden beneath the pool floor. These joints act like giant shock absorbers, allowing the pool to flex up to 500 millimeters in any direction. Furthermore, the entire pool structure is leveled by over 500 adjustable jacks to ensure the water surface remains perfectly level, regardless of how the buildings settle over time. While the towers were rising, another icon was taking shape at their feet: the Art Science Museum. Designed to resemble a blooming lotus flower, its 10 petals are framed by high-tech reinforced polymer. This structure posed its own set of geometry challenges, with no two petals being the same size or shape. The museum uses a steel lattice skin to support its unique form, creating a massive internal space without the need for central pillars. At the center of the lotus, a waterfall feature collects rainwater, recycling it for the building's internal plumbing. This project proved that Marina Bay Sands wasn't just about height, it was about pushing the boundaries of organic form through digital precision and advanced materials. Living on the edge of the Pacific means the structure must endure tropical storms and high-altitude winds. To test the design, engineers built scaled models and placed them in wind tunnels, simulating the most extreme typhoons. They discovered that the Sky Park actually acts as a massive wind damper, helping to stabilize the towers. However, the wind loads on the glass cladding were still immense. Over 12,000 unique glass panels were used, each engineered to withstand pressure and thermal expansion. The building also features an advanced building management system that monitors wind speed and direction, automatically adjusting the HVAC and ventilation systems to maintain stability and comfort for the guests inside. This glass and steel. The construction timeline was as aggressive as the design itself. With a workforce of over 16,000 people on site at its peak, the project was a 24-hour operation. Logistics were handled with military precision. Every crane movement and concrete delivery was scheduled to the minute to avoid bottlenecks in Singapore's dense urban environment. The project faced a global financial crisis midway through construction, threatening the funding. Las Vegas Sands had to navigate a treacherous economic landscape to keep the dream alive. Despite these hurdles, the complex was completed in just under 5 years, a testament to the sheer willpower of the thousands of engineers, architects, and laborers who turned a sketch into a global landmark. Today, Marina Bay Sands stands as a symbol of human ingenuity and Singapore's meteoric rise. It transformed a patch of reclaimed mud into the world's most recognizable resort. The construction proved that with enough innovation, we can overcome the most daunting geological and physical constraints. From the deep diaphragm walls to the flexible infinity pool and the gravity-defying sky park, every inch of this structure is a testament to the power of modern engineering. As we look to the future, the lessons learned here continue to influence how we build our cities, reminding us that the only limit to our architecture is the depth of our imagination. The impossible is now a permanent fixture of the skyline.